So let's continue with a lesson that began some time ago. This is about stellar radiation and stellar types. So here we've got all the stars from the smallest through to the biggest and hottest. There's actually more than this OBAFGKM scheme, but we're just going to stick with this for now because that's all the IB requires. What you do need to know is that in between the O and the B, there are stars, namely O1, O2, O3, O4, O5, all the way up to O9, and then there's B1, B2, B3, B4, all the way up to B9. Actually, it starts at B0, B1, B2, and so on. And anyway, there's colder stars than M, but we're not going to worry about the stars that are colder than M. We might not even get to actually this list of stars today. We'll see how we go. I'm just going to talk to you for about 25 minutes or so. We also mentioned last time that there's something called the PP chain, and the PP chain is a way that stars generate energy by fusing protons, that's the P and the PP, into helium. And so a helium nucleus has 2 protons and 2 neutrons. So we'll talk about that in more detail soon as well. And these are the things we're going to try and explain today using some physics, namely how clouds of gas, by which we mean hydrogen and helium, condense down into things which are able to fuse, which we call stars. So a cloud that is not fusing is not a star. A cloud that is fusing is a star. So there's a difference. Well, actually, you can have something in between a cloud and a star, and that might be something like the planet Jupiter. And so it is a sphere of gas, the center of which is hot, but not hot enough for fusion to take place. So what happens when a star is born? Well, all stars start life as a nebula of gas and dust. And remember what I said about gas? It's hydrogen and helium. What is dust? Everything else. Okay, so over millions of years, gravity pulls these closer together. Now, where these clouds of gas, where these nebula come from, is one of 2 places. Number one, they were just there at the beginning of the universe. So the universe exploded in a big bang, and so we had hydrogen and helium in roughly the proportions of 74% to about 25% hydrogen and helium, and there was a tiny little bit of other stuff, but basically nothing heavier than lithium really. And over, well, about the next maybe 1 billion years or so, we had the first stars being born. Once that first generation of stars were born and then died, the explosions released lots and lots of gas into the universe, and so some of the remnants, some of the leftover stuff from those exploded stars, they turned into nebula as well, and then you have a second generation of stars, and so stars that explode leave behind their basically spewed up guts throughout the universe, and it's those things that can be then condensed into new stars. And so you have second generation stars, third generation stars, and so on. The older stars really are third generation stars. We'll talk about that again some other time as well. So the birth of a star. Here's basically what happens. You have your big cloud of gas. Gravity pulls inwards on the big cloud of gas, and it causes the cloud of gas to contract towards the center. And as a cloud of gas is compressed, the laws of thermodynamics tell us that the temperature goes up. Okay, so pressure builds up and the core starts to heat up, giving out infrared radiation. So you've just got this force inwards of gravity. A star is born essentially when fusion begins. So you have this spherical object before fusion begins that astronomers give a special name called a protostar. Now, a protostar isn't something that fusion is taking place in, but nor is it a thing where fusion will never take place. So, for example, something like Jupiter is not a protostar. It's a planet, but it doesn't matter how long you wait. Although it's hot in the center, Jupiter is not going to have fusion starting in the center of it. It's just not big enough. So for a protostar, the dust and gas from the nebula is added to the protostar. It gains mass. As mass is gained, gravity increases, and the temperature within the protostar increases. So it's a sort of a simple process. Gravity causes the thing to collapse. The temperature heats up in the center. The temperature heats up to a point where you get, well, basically ignition occurring. And the ignition is the point where the star is born. So the gravity eventually gets so big and the temperature gets so high that nuclear fusion starts. It becomes a star. Life of a star. Let's see what happens. There's a nice picture of the sun. A star is in a state called hydrostatic equilibrium. And in hydrostatic equilibrium, you have a balance of two forces within a fluid. So we can call the roiling hot mass of spherical plasma that is a star a fluid. Okay, roughly speaking. The fluids are basically liquids and gases, and for all intents and purposes, stars are gases. Sometimes we give them fancy names like, oh, it's a plasma state, but basically a gas. The mass of the star has lots of gravity. The gravity is pushing in, but at the same time, there is an equal and opposite force pushing out from the center, and we give that a name, and that's called the radiation pressure. And what's going on is right in the center, fusion reactions are like lots and lots of hydrogen bombs going off, and they're exploding in the center there and causing huge amounts of energy, and the energy is flying outwards from the center of the star in the form of radiation and also in the form of particles. And so you have this balance, this lovely little balance in a normal star, or what we are going to start calling a main sequence star. A main sequence star is where you have hydrostatic equilibrium and the burning of hydrogen. The force of the radiation pressure from nuclear fusion is balanced with the gravitational force in a stable star. So, nuclear fusion, essentially for now, there are many, many variations on this kind of reaction, but here's the most important one. It's from that PP chain, which says that if you take 4 hydrogens, then you can create a helium, and that puts out some energy as well. And that's the secret behind some good 90% of stars that are up there in the night sky. The death of a star. Stars don't last forever. They burn fuel and then eventually they exhaust all of their fuel, and a number of things can happen that we've already seen. So there are 2 ways that a star can start off. It can start off small, like our sun, or it can start off big, like this star over here. They are of different sizes. Now, if we're going to actually consider big stars at the beginning of their life, they're probably going to be blue, not red. See how big a red giant star is, though, compared to something like the sun and something like the Earth. A red giant is kind of inconceivably large. Just think about how big the Earth seems to you right now. So, a red giant. Eventually, a star becomes, the size of our sun becomes a red giant. And why? Because it's run out of fuel in the center. And once it runs out of fuel in the center, then it collapses because there's no longer any radiation pressure outwards. Because there's no radiation pressure outwards, the star collapses under gravity, and that can ignite a new sort of fusion, which is called, well, hydrogen burning. And long story short, the hydrogen burning occurs at a temperature about 10 times that of, the helium burning occurs at a temperature of around 10 times that of hydrogen burning, and so the entire thing expands until it's huge. But eventually even that fuel source runs out and the whole thing collapses, like we can see here, until it turns into a white dwarf. And a white dwarf is a star, in inverted commas, because, in scare quotes, because it's not really a star, because the definition of a star is an object where fusion is occurring, but in a white dwarf you're no longer getting fusion. Instead, what you've got are the hot ashes left over from a burning fire. No new combustion taking place, the thing is just cooling down. So, white dwarf eventually cools down to become a black dwarf, wandering through the universe cold and alone for the rest of its existence, in the existence of the universe, so far as we know. Next, larger stars. So stars bigger than the sun. This is a bad choice of colour. That star should have begun as a white star, not as a red star, but oh well, mistakes happen. Okay, so this hot white or maybe even blue star, once it runs out of hydrogen, then it collapses and it starts to burn helium and gets bigger, but eventually the helium runs out, and in fact what happens is the helium turns into carbon, then the carbon runs out, and the carbon can create, via a complex series of reactions we don't need to learn about in the IB, I had to sit through it in university lectures, but basically the carbon turns into nitrogen, turns into oxygen, turns into phosphorus, turns into silicon, and so on up the periodic table. And each time it goes through a new cycle of creating some new kind of element, the thing has to get bigger. And the thing has to get bigger because the temperature required in order to fuse these larger nuclei causes the gas to expand. And so you just get bigger and bigger and bigger red giants. And so they give them a special name, red supergiant, right? Eventually, even that fuel source runs out. The reason that fuel source runs out is because you get up to iron on the periodic table, number 56 from memory, and at number 56 you can no longer have fusion taking place which causes an exothermic reaction. Instead, the fusion of iron, or the fusion of things heavier than iron, requires energy. And so the entire star collapses because no new energy is being produced, just as it would be in a white dwarf. The reason why a white dwarf doesn't collapse any further than what it does is because you have maximum compression of normal matter. So atoms are buttressed up against atoms as strongly as they possibly can be. But there is something stronger than the interatomic forces between atoms, and that force is gravity. Okay, so given enough mass, you can have a gravity which exceeds the structural integrity of the atoms, and so the atoms themselves will collapse, and they will head inside one another. And so that's what we're about to see on the next slide, which is when atoms go inside of one another. Essentially what that means at the level of the atom is that electrons go into the nucleus. And where do they go? They go into the protons. Electron plus proton is neutron. And so any neutrons that are in that nucleus to begin with, well, they remain there. But now the protons turn into neutrons, and so all you have is a neutron at the center of such a star. And then the neutrons are buttressed up against neutrons, and no further collapse takes place. Unless you have an even more massive star. If you have an even more massive star to begin with, then you have so many neutrons all buttressed up against one another that even the structural integrity of the neutrons is insufficient to prevent further collapse. And the neutrons start to go inside of neutrons. And at that point you have this thing called a singularity, where everything goes inside of everything else, a point of high mass in zero space. So you have infinite density, because remember, density equals mass divided by volume. So if you have zero volume, you're dividing by zero. No one's allowed to divide by zero except for Chuck Norris or God, or in this case, a black hole. Sorry, I'm just sipping my coffee. A neutron turns into a pulsar. Now, why is this? Well, as the thing collapses, the thing starts to spin really, really fast. And that spinning is stars give out radiation, right? And so all stars give out radiation. They give out radio waves, they give out X-rays, they give out all sorts of, electromagnetic frequencies. And in the case of a neutron star, as the thing collapses, it tends to funnel, it tends to focus all of the radiation into two beams. And as the thing spins really, really, really fast, those beams sometimes get directed towards the Earth, and we can pick them up with radio telescopes. And so when these things were first discovered, and you can look up the famous female astronomer Jocelyn Bell for this, and Jocelyn Bell was the first one to discover this object called a pulsar. And so she pointed radio telescopes at the sky and noticed that there were pulsations coming from certain parts of the sky in the radio frequency, and so called them pulsars. And later on, they were found to be signatures of neutron stars. So pulsars are neutron stars, and so far as we know, all neutron stars are pulsars as well. If a star is large enough, it'll become a black hole. Okay, and so a black hole is of zero size. However, although the black hole, all the mass is concentrated into a region of zero size, the gravitational field around the black hole extends to this point called the event horizon, and we'll talk about that later. So the black hole, the hole itself is zero, but the region of space around it, where it's dangerous to be, extends further than zero. So these black holes have radiuses, right? They have radii We'll talk about that another time, though. Alright, so the important thing for this lesson at the moment that I just want to get across is that there's this equilibrium between radiation pressure and gravity. So the pressure out equals the gravity in. That has a name, it's called hydrostatic equilibrium, and that's why stars are spherical, that's why stars are stable, that's why stars don't just blow themselves up even though they've got these hydrogen bombs going off in the centre, and nor do they collapse even though they are massive and gravity's sucking them in. This is the last thing I'll do for now. I think I've talked for long enough. A little bit shorter than I thought, but I think you can do a little bit of reading after this. Luminosity. Luminosity is how we measure the total power output of a star. Okay, so it is one of the biggest measures that we have, or one of the most precise measures we have for determining the differences between stars. Some stars put out lots and lots of energy, some stars don't put out much energy. So luminosity is not like apparent brightness. So when you go out into the when you go outside at night and look at the sky, then you notice that some stars are bright and some stars are not bright. The brightest star that you'll see in the sky is something called Sirius. The next brightest star is something called Canopus, and the next brightest star again is something called Alpha Centauri. Well, actually, the brightest star that you see in the sky is the sun, right? You won't see it at night, of course, by definition. But the point is that the sun is extremely bright, but it's not very luminous compared to other stars. The only reason it seems bright is because it's so close to us. And so this should indicate to you the difference between something called apparent brightness, okay, apparently how bright is the star, and something called luminosity, which is how much total energy the thing is giving out. And so the sun gives out a certain amount of light in total, and that appears a certain brightness in the sky. And so this idea applies to every other star that you see in the sky. So the really bright ones you see in the sky, you don't know just by looking whether or not they are close and actually dim, or a long way off and actually really powerful, really, really bright. It's impossible to tell just by looking in the sky at night. You need to have other ways of calibrating exactly how bright those stars are. Now, the way that you do that is in part based on the parallax method that we've already talked about. So seeing if the stars move on the sky at all, then you can find a distance to them. Once you've found a distance to them, then you can figure out, okay, well, that star happens to be 10 parsecs away and it also appears to be this bright. Once you've got those two things, once you've got the actual distance and the apparent brightness, then you can figure out the true brightness or the luminosity. Okay. Anyway, for now, luminosity is the same quantity as power, the same as watts. Okay. So power is work divided by time, energy divided by time. So is luminosity. Okay, energy divided by time. How much energy an object, in our case a star, but it could be a candle, it could be a light globe, how much energy it's giving out per unit time, per second. Okay, final thing. Okay, I promise this will be the final thing. Black body radiation. Here's a lovely picture of a metal worker, blacksmith, who's heated up some iron and is now shaping it. Okay, heated up to red hot so that the iron is all bendy, and what we notice is that it's changed colour and it goes red hot. Now, in common everyday English, we talk about things being red hot as being the hottest. In astronomy, you have to undo what you've learned before, and although you might think blue is nice and cool and red is very hot, you've got to reverse that in your mind now, okay? Because from now on, in astronomy, red is the cool one, blue is the bleeding hot one, okay? And so the colour scheme actually goes red, orange, yellow, getting hotter, white, and blue. So it's all the colours of the rainbow except for green. Okay, green is a bit of a mystery. Now, I'll have to do a separate lesson on why there are no green stars. Okay, it's complicated. We have to approach it from a few different directions. And white is not actually a colour of the rainbow, but there's a clue, right? What should be green actually appears kind of white. Now, Why is that? Now, are there violet stars or purple stars? Well, kind of, sort of. It's just that our eyes don't pick them up. Okay, our eyes happen to be really sensitive in comparison to blue, and so a star that should appear to be purple appears to us to be blue. Yeah. Okay, so we might have mentioned this before when we did some stuff on quantum theory, and we might have mentioned this, and also stuff that we did in thermal physics, we might have mentioned this. This is called a black body radiation curve, and we're going to get onto a law called Wien's law, not today, but it explains how, and this is a particularly poorly drawn graph, and can you spot the error? Okay, I'll leave that as a question for you to answer, but there's a misconception here with this graph, or a poor choice here for something. You can think about it, but the point here is that on this axis you have energy being put out, total energy being put out. Okay, they're called the energy density, but total energy being put out by an object. And here we have the wavelength. So if the thing has a really high temperature in comparison, let's say 2000 Kelvin, okay, which isn't really that high, but it's high enough in comparison to, let's say, 1750 Kelvin or 1250 Kelvin, we notice a couple of things that are different between these objects. So I have three objects here plotted. One is 2000 Kelvin, one is 1750 Kelvin, one is 1250 Kelvin. The graph that you get for this one here, for the highest temperature one, has a peak. If we draw a vertical line downwards, so it intersects with the x-axis, we get a number that is somewhere around about 1000, let's call it 300 nanometers. What does that mean? It means the peak radiation, the wavelength that is being most of the radiation is coming out around 1300 nanometers. So that's one thing we can say about this graph. For the 1750, if we drop a vertical line downwards, it's no longer down here at 1300. It's a little bit further to the right. It's like, I don't know, 1500. And for the 1250, it's a bit harder to tell, but let's call it somewhere over 2000 nanometers. What's the point of all that? As the temperature goes up for an object, the peak of the radiation has a shorter wavelength. Shorter wavelength means higher frequency, higher energy. So the difference between objects with different temperatures is that the peak wavelength of the radiation gets shorter. That's one difference between each of the graphs. And the other difference between each of the graphs is that the total amount of energy between objects with higher if we compare objects of higher temperature to objects of lower temperature, the objects of higher temperature put out far more energy overall. So it's putting out more energy at every single wavelength. This one here of 2000 Kelvin, this one here of 1750 Kelvin is putting out less energy at every single wavelength. What are the problems with these graphs? Okay, that was my question I was leaving you with. What's a black body? A black body is just anything that emits all the radiation that it absorbs. Okay, that might be another question I'll leave you with. So that's where I'll stop for now. I've written a few questions, okay, one of which, let's just answer, is what's the problem with this graph? Another of which is look up what a black body is and write down a definition for a black body. And I'll write a few other questions for you to complete for this lesson as well. And see you next time.